what's going on? 4./0. I cannot get. Oh, okay. Yeah. Let's see. Okay, maybe this. Okay. So yeah, we finished our midterm. So let's get back to Laplace transform. So a quick review about Laplace transform. Once again, Laplace transform, we start with thinking it as analytical continuation of Fourier transform. So basically, the idea was we said that the eigenvalues of LTI systems are those e to the st, and those s can actually be complex number instead of purely imaginary. So we think about what happens when we have purely imaginary s. So so we write the Fourier transform equation with s being arbitrary complex number, and we see what happens. And we think we can just define this thing as some function big X of S. So this is consistent with the previous notation where we had big X of j omega. So for Fourier transform, we had big X of j omega. And now you can think about Fourier transform as a special case of Laplace transform, where S is purely imaginary j omega. And then we see our favorite function. So this is exponential decay function e to the minus a u of t that you also see many times in meter. And so its Fourier transform is 1 over j omega plus a. And its Laplace transform is very nice. It's just 1 over s plus a. But so we want to try this for every s, but we found out that it doesn't converge for every s. So it only converges for s that has a real part bigger than minus a. Okay, and then we see that this region of convergence, meaning that what value of s is converged, is actually very important for Laplace transform. So next we see a function that looks totally different. Is minus c to the minus at u of minus t. So this thing only converge. Well, not quite converge, but also only looks absolutely integrable if a is less than 0, and it's kind of exponential decay to negative t. And because you have the u of minus t, so this is cut over t, so this for t bigger than 0 is all 0. And so this is a quite different exponential decay function. We found that it has the same algebraic expression, Laplace transform. So you do Laplace transform, is also 1 over s plus a. But then its region of convergence is that the real part of s is now less than minus a. And we see that it has those nice pictures. So both of those things is 1 over s plus a. So it has this pole or singularity at s equal to minus a. And one of them has right-sided ROC, and the other of them have left-sided ROC. Okay. And ROC is a very important concept, which we will go over today, about properties of ROC. So this is this is something we don't have when we talk about Fourier transform. It's only in Laplace transform we need to think about those ROC, and we just think from this example that ROC is a very important part of the description of Laplace transform. If you have the same expression for your Laplace transform, but you have different ROC, then actually they correspond to different function in a time domain. Okay, and I think that's right. Then we talk about rational functions. And so rational functions are a polynomial of s divided by another polynomial of s. And since they are polynomials, they are basically determined by their roots. Right? So by the fundamental theorem of algebra, you can always break polynomials into monomials with some complex roots. And Well, if you know the roots of n, the numerator, and the roots of d, the denominator, then you basically know this thing up to a constant. So you can determine all the property from the roots. So we like to draw the roots on the x-plane. So we draw the roots of the denominator as a closed. So those will be the poles of x of s is a point where x of s is going to infinity. And of those draw zeros. So the roots of n of s with a circle on the plane. And then we usually draw ROC with those shaded area. And I guess if you draw with like a actual pen, then you can do such lines, etc. But yeah, so those are the pole zero plots with ROC. And also we think about at infinity can be zero, or the infinity can also be a pole zero. So it depends on whether x of infinity is infinity or zero. Okay. Okay. And okay. So yeah. So now we're back to the properties of our ROC for Laplace transform. So this is the first topic. We kind of go through this very quickly this time, but now let's go through those carefully. So the first property is the most important one. So it says ROC of the ROC consists of strips parallel to j omega axis. So it consists of sets of straight lines. And this property really comes from something we didn't quite prove. And it's a bit tricky. But we think for a given sigma, so the real part of S, for a given sigma, the x of sigma plus j omega is a Fourier transform of x times e to the minus sigma t. And and we just think this thing either converge for O omega or doesn't converge for O omega. So this line is a fixed. This line is a fixed sigma, and we think about how does the convergence go for different omega. And we think that well, those are Fourier transform for different omega, but your Fourier transform either converge for O line or doesn't converge for O line, usually. So this line should either be O convergence or O non-convergent. Okay. So that's the idea. Yeah, so here we are kind of ignoring that you might get some delta function in some point, etc. Generally, we think that it will converge on the whole line or not. And yeah, and if you want to see the details, the book has some reference to mathematical books, to more mathematical books, and you can read the more rigorous arguments in mathematical books. But this is what we will believe for Laplace transform. And also, this is really a stronger condition than property 1, and which we will use. So we say that because we think this whole line is the Laplace transform of this whole line is the Fourier transform of e to the minus sigma t, and we give condition for this this Fourier transform being convergent, and we say this is converge if this whole line is absolutely if on this sigma this this function is absolutely integrable, and yeah. So this makes some sense because this is one of the directional condition, and we say that if your x is not weird, then the Fourier transform should converge. Okay, so here we are kind of assuming our x behave nicely, so don't have too many maximum, minimum, etc. And yeah, anyway, this is a condition we'll use later. So we think that if at this sigma, this x of t e to the minus sigma t is absolutely integrable, then very likely the Fourier transform will converge, and so your Laplace transform is converge on this line. Okay. And okay. And okay, so if there is no question, then let's see the next property. So property 2 is just says that for original Laplace transform, so there are poles and zeros, then your ROC doesn't contain any poles. And it's very simple because as we say, the poles is where your x of s goes to infinity, and if it's infinite, obviously it doesn't converge. So the Laplace transform doesn't converge on pole, then the ROC should not contain that pole. Okay. And then property 3. Property 3, it seems a bit trivial, but actually not actually useful sometimes, as we will see. And it says that if your x of t is finite duration and absolutely integrable, then your ROC is the entire S-plane. So it's easier if we just see the picture first. So here is what we mean our finite duration signal. So it starts with some t1 and it is on t2. And it's a 0 or otherwhere, outside everywhere. And it's absolutely integrable, so the middle, it can still go to infinity, but doesn't too much. So yeah, so it's relatively behaving well in between these t1 and t2, so integrate this is good. And okay, so you have this very finite, very controlled signal. And so what does your ROC go to entire S-plane? Then this is where we use this condition. And so we are using that if x of t satisfies this, then at last sigma, your last sigma is in your ROC. Right? So from party 1, we just, if you want to specify ROC, you just need to think about what sigma is in ROC. Because you determine a sigma in ROC, then the whole straight line with that sigma is in ROC. And yeah. So, and then we can use this to argue for whether different thing to think about. So we just multiply your x of t with e to the minus sigma t and think about whether that thing has Fourier transform. Well, your x of t look like this. Then you can multiply different sigma e to the minus sigma of t. So depending on whether your sigma is bigger than 0 or smaller than 0, you get an exponential growth or exponential decay multiplying your signal. But your signal is behaving very well, so if you multiply by exponential decay or exponential growth, then it still looks relatively well. Like you can get a bit higher, so you get like e to the minus t1 sigma here or e to the plus t2 sigma here, but it's still some finite value, so you're just multiplying by some finite value. So these two things should still be absolutely integrable for any negative or positive sigma. Yeah, so just from this intuition, we think your x of t e to the minus sigma t. So okay, let's write things here. So this is our x of t. Then we think about what happened to x of t e to the minus sigma of t. So this one should be sigma bigger than 0, and this is sigma less than 0. And we think that they are still pretty well behaved, so they should both be absolutely integrable. And that means for any sigma, your Fourier transform converge, and so they are in ROC. And so we can see, excuse me. So we can see more rigorous mathematical proof. So we start with saying that our x of t is from t1 to t2 and it's absolutely integrable. So integrate from t1 to t2, absolute value of x is some finite value. And now we think about where s equal to sigma part j omega is in ROC. And then from property 1, we just need to check this sigma. Okay. And we prove that for any sigma, it should be in ROC, so we check x of t times e to the minus sigma of t. And we see whether this is absolutely integrable. And then there are really 3 cases if you are really careful. So first case is s equal to 0. Then obviously that works because s equal to 0, then you just back to the first equation. So that's finite integral. The integral result is finite. And then there are 2 cases. For sigma bigger than 0, then we are kind of getting this, right? And then so right, what we had in the equation, so we have x of t times e to the minus sigma t dt. And then we think about this e to the minus sigma t is an exponential decay function. So the biggest value is at this t1 value, right? This decay function is biggest at t1. And everything is positive here because we are doing absolute value. And so you can take the largest one and being upper bound. So this is less than just the original integral times the largest value of e to the minus sigma t between t1 and t2, and that's e to the minus sigma t1. Okay, so it's less than this value, and we know the second part is finite from the first equation, and this is also some finite value because well, you have if you have some sigma and some t1, this is just some number, so it's also finite value. So for every sigma, this is a finite value. Sigma bigger than 0, this is a finite value. So for every sigma bigger than 0, your x of t to minus sigma t is absolutely integrable, and so that s, the corresponding s, is in your ROC. Okay, so ROC for every real part of s, it means sigma bigger than 0, is in ROC. Okay. So this is bounded, and this is bounded. And so similarly for sigma less than 0, we have the same argument. So it's now this thing, and you have the exponential growing function, and the biggest value is at t equal to t2, but this is also a finite value. So also for every real part of s less than 0, your Fourier transform always converge, and so that point is in your ROC. Okay. So we see that for every sigma, every sigma is in your ROC, so your ROC is a whole plane. Okay. Any question on this proof? Okay. And so this is okay. Oh, sorry. We have example. Okay. Example, so we have x equal to e to the minus at between some finite region, right? Because we want to have a finite duration signal. So draw this like this. So x is between 0 and big T, and it's e to the minus at can have a, actually a can even be complex, but let's say it's a real number. So real positive number might be more common. Okay, so if a bigger than 0, it look like this. So finite duration x of t, then it's 0 outside. Okay, so x of t look like this. And okay, so this is finite duration, so your RC should be everywhere. Okay, and it's actually a bit tricky. So if you do the brute force calculation, so x of s, so you run the Laplace transform equation, so x of s equal to e. Your x of t e to the minus st, then integrate from t minus infinity to plus infinity, but cut off from 0 to t. And so you do this integral, well, there you have the exponential here, then you get 1 over s plus a, 1, and then 1 minus e to the minus s plus at. Okay, and okay, so that's your Laplace transform, but then you think this equation looks a little weird because it should be convergent on every s, right? But you have this one raised over a here, one raised plus a here. Then you think either one raised plus a has a pole at s equal to a, okay? And yeah, then that's troublesome. It should converge on every point. But what if a is equal to, sorry, not a is equal to a is equal to minus a? So isn't there a pole here? And so the answer here is that, well, yes, it has a pole here, but also it has a 0 here, and they will kind of cancel out. Okay, so the upper part we have this weird 1 minus e to the minus s plus a t. And so you have s equal to a, then this part is 0, so you have 1 minus 1. Okay. So you have 0 over 0 at s equal to minus a. And then, yeah, so if you want to find the actual value of this x over s at your pole, then we can use our calculus, then do a Laplace rule. So we do differentiation on both the upper side and lower side. So dds, and dds is just 1, so then on the upper side you should get this thing. Let's see, it's correct. So this 1, you do differentiation, it goes away, and then you get minus t here, okay? Minus t times minus sign, so you get plus t, and then the exponential here. And the exponential part, when you take s equal to minus a, it just becomes 1, so then you have x over minus a equal to t, so just this big T here. Okay, and yeah, so now we believe, so this is actually a finite value, so now we believe that what we had is true. So we have the finite duration, absolute integrable x over t, and its Laplace transform is convergent from on every s, even though it has this 1 raised over a, it looks like a pole at minus a. Okay, question? Yeah, so this also tells you that when you think about the point zeros, you need to be a little careful. There might be some cancellation. Say if you are, for some reason, like even for your rational function, then you get like s plus 1 over s plus 1, then it's really not the pole 0 at the minus 1 because you can cancel, then it's just equal to 1, etc. Okay, that's a little trivial. Okay, so that's a finite duration function, and they're very nice. They converge, their Laplace transform converge everywhere. You might think it's a little too specific, but let's see a less specific function. So what if we have a right-sided function? So it means like a function looking at this. So for the finite duration function, it has the left side cut off at t1 and right side cut off at t2. But now we have a right-sided function, so it has a cut off at t1 on the left side, and on the right side it can be anything. And so it kind of a half of the constraints of the two-sided function, okay, of the finite duration function. And so if x over t is right-sided, then ROC also has some property because of this cutoff at t1. Okay? And so it says that well, the idea is really the ROC will also extend it to the right side to infinity. And so in the more mathematical description here, it says that if some line at sigma 0 is ROC, then all the right side of sigma, all the right side of that sigma is also in ROC. So every bigger sigma is in ROC. That means your ROC should extend to right infinity. Okay. And well, then the proof is really similar to the proof we had here, right? So it's right-sided, so only one of the exponential thing work. Okay, so we think about how this thing multiplying with the decaying exponential work. So you have this thing multiplying a decaying exponential. Then once again, the exponential get biggest value at this t1. Okay, and oh, okay, so yeah, okay, so this is a little more, excuse me, yeah. So not all decaying exponential will make this finite because we didn't say x of t is we didn't say x of t is absolutely integrable or anything. Okay, so so this is a little more tricky. So your x of t can be something like let's draw this. So it has a cutoff of t1, but different from before, we didn't have that x of t is absolutely integrable. So x of t can be anything. So x of t can be maybe this thing, right? So x of t can be divergent by itself. So we don't have that for every RES, like for every sigma bigger than 0, it will converge. Because your x of t might be diverging by itself, then you need a stronger decaying exponential to cancel this out, so your whole signal will be converged. But the idea is that you have if your x of t times your e to the minus sigma t, right? So we think about we are multiplying e to the minus sigma t. So your x of t times e to the sigma 0 of t is already absolutely integrable. Then you are multiplying with even stronger decaying exponential, then it should also be converged. Okay? People buying this? And that's why we have this condition here. So for every sigma 0, if it's converging, then you have some sigma 1 bigger than sigma 0, it should also be converging. Okay? And okay, so the mathematical form is like this. So if you are okay, so we are so we are really thinking this being okay, so maybe we should go back to property 1. Okay, so this doesn't, so we are back to using this thing, and we were a little vague about this. So we say if this is satisfied, then it's converging. But what we are assuming, if this is assuming, is that this is like if only if, right? So it doesn't seem very rigorous, but this is what we assume. Okay, so we are thinking sigma is in the ROC if only if this thing is absolutely integrable. Okay, and so that's why we can have this thing here. So we think sigma 1 is the ROC, and then that means this is absolutely integrable. And okay, okay, and the opposite is right-sided, so this integration we can cut off at t1. And so we have some sigma 0, this is converging. Then we think about we change sigma to some sigma 0 to some sigma 1, that's bigger. And well, so this sigma 1 can be written as sigma 0 plus sigma 1 minus sigma 0, and then you break the exponential like this. And then the extra part is another decaying exponential because sigma 1 bigger than sigma 0, and this decaying exponential is biggest at t1, right, because it's decaying. Okay, so this is less than this e to the minus sigma 0 times minus sigma, excuse me. This is upper bounded by the previous part times the maximum value of this exponential, which is e to the minus sigma 1 minus sigma 0 t1, and whatever. So this might be a big value, but since t1, sigma 1, sigma 0 are all fixed values, so this is just some number. And so this is finite value, and this is finite value because by our assumption, so this whole thing is finite value. And so we know that for sigma 1, so this is finite value and it is bigger than this thing, so this is also finite value. So this at sigma 1, your x of t to a minus sigma 1t is also absolutely integrable, and the Fourier transform is convergent, and so it is in the ROC of your Laplace transform. Okay. So similar argument. Question. Okay, so that's right-sided x of t, and obviously we have left-sided x of t. Okay, so here are some picture. So where sigma 0 is a decaying exponential, e to minus sigma 1 is a higher rate decaying exponential, and things can really only blow up at infinity. So if you are decaying faster to plus infinity, it should also be converging. Okay. And similarly, we have left-sided x of t. Then your ROC should extend to negative infinity. And it's really similar, so I think we skip a proof. Here is a picture, so your x of t is left-sided, so it's cut off the right side as on t2, and they are thinking about multiplying negative sigma. Yeah, so this line once again is our e to the minus sigma t. E to the minus sigma t with a negative sigma, so it's actually a growing exponential, but it's decaying to this negative infinity part. So if you are putting a smaller or more negative sigma, you should decay even faster to a negative infinity part, and so they will always converge, and so your ROC will look like this. So whenever you are converging at some sigma, this left side is also converging. So left-sided x of t has this going to left infinity ROC. Okay, question? Okay. And okay, so you think about those property. Wait. Oh yeah, 3, 4, 5 all looks like pretty restrictive function, right? So it's either cut off two sides or cut off right or cut off left. So they are pretty special functions. Actually, you can piece them together to get something really cool. So this is property 6 that we don't quite prove before. So it says that if now your x of t is two-sided, so basically really just whatever function, then your ROC only have one stripped. Okay. Yeah. So it says that you have some. Okay. Yeah. So this sigma 0 doesn't really mean anything. So if something your ROC, then your ROC will obviously contain this sigma 0. But really, what does it say is your ROC. So we say ROC is a collection of sigma, but this really say your sigma only has one interval can be your ROC. So you cannot have multiple strips. Only have one strip to be your ROC. Okay. And yeah, so we have some schematic here. So your ROC is either like bounded by two sides, or like some one strip in the middle, or you can extend to plus infinity or extend to negative infinity. Well, it's not quite this. Okay. Depends on how strict you want to be on your two-sided. So as we say, this ROC really correspond to right-sided function, and this really correspond to left-sided function. So there are some weird thing. Yeah, but anyway, what we are ruling out is you cannot have two separate strips for your ROC. Okay. So your ROC only need to have one strip for any function. And anyway, let's see the proof first. So we used in our property before. So we have this two-sided function, then we can cut it up into two functions, right? So we can pick whatever value t0, and we cut it into right-sided function and the left-sided function. Okay, so our original function is sum of this one, the right-sided one, and the left-sided one. And yeah, and then the left-sided function, sorry, the right-sided function, you should have ROC to the right side, right? Because we just proved it. And the left-sided function should have ROC to the left side. And the ROC of the original function should be the intersection of ROC of both, right? Because you want both of them to converge. Okay, so to the right, to the left. And yeah, so the ROC of both should be one strip in the middle. Okay, so that's the idea. And so this tells you that yeah, so this tells you that your x is two-sided, then your RC should really so or more like your x for the general function, your RC should really have one strip, because you can think about it's left side one plus the right side one, and one of them will extend to the left and one of them extend to the right, and if you take the overlap of those two things, you can only get one strip. Okay, or obviously there are some cases where there is no overlap, so you get no RC. Okay, and then let's see an example of this happening. So our two-sided function now is x of t equal to e to the minus b absolute value of t. We kind of see this multiple times in Fourier transform. And look at this. So it's two-sided exponential decay. And well, we didn't say b yet. So there are two cases. So there are b bigger than 0 or b less than 0. Obviously, you can also have b equal to 0 with a straight line. Let's forget about that for now. Okay. So for b bigger than 0, then it's exponential decay on both sides. And for b less than 0, then it's exponential growing on both sides. And you kind of think, I guess intuitively you will think this is very divergent and it will not converge anywhere. And that intuition is correct. But for now, let's do this with the algebra and see that what happens. And so as we said, we want to cut this two-sided function into a right-sided signal and a left-sided signal. And t1 can be anything, but obviously there is a t0, t equals 0 here, seems like a very good cut. So we cut it at t equals 0, then you get this plus-sided, right-sided exponential decay and the left-sided exponential decay, and the cut we write it with u of t and u of minus t, as usual. And okay, then we do Fourier transform on both sides. So this is right-sided, so this is e to the minus bt u of t. As we just reviewed today, its Fourier transform is 1 over s plus b, with the ROC bigger the right side of minus b. Okay, and this satisfy our expectation. So it's a right-sided function, and the ROC is to the right side. And then we also have this e to the plus b. So for the negative part, so e to the plus b, because t negative is absolute value sign to get the extra negative sign here. So e to the plus b u of minus t. And we didn't have this before, but we have I think we had example 9.2 that was the minus e to the minus bt u of minus t go to 1 over s plus b thing. And yeah, so sorry, it is u of minus t, right? So we have this also go to s plus b, and if you do some changeable variable on this thing, and yeah, actually we can see the changeable variable here already. So you have plus b to minus b, so you get extra negative sign on b, and you have the extra negative sign here, so you get extra negative sign here. Okay, and okay, so let's write down our C here. This is E is less than minus b. Okay. So you do change your variable around this thing, then you see that this corresponds to this -1 is -b, and then because you have plus b and negative b here, so RE is less than -b become RE is less than plus b here, okay? Because you have a negative sign on your b, okay? So yeah, you can do some change your variables on this, and then you get this this Laplace transform pair. And now we think about what's the ROC when you add up those two sides together. So there are really there are b bigger than 0 or b less than 0, less or equal to 0. So b bigger than 0, then it's a good thing. So the first one you will have RES bigger than negative b. So the first one should go like on the right side of this negative b, so this part. And then the second one you have RES less than plus b. So on this part, so the overlap is the middle, this -b to plus b thing. And your algebraic part is you just adding those two algebraic parts together. So for b bigger than 0, you have this nice Laplace transform of 1 over s plus b minus 1 over minus b. Then ROC is between negative b to plus b to positive b. And then if you have b less than or equal to 0, okay, so the picture is actually quite wrong, because it was copy paste here, so we should not have any ROC. Okay. I don't know how to do this, so maybe so we need to I guess I will just say, so imagine this is empty here. But anyway, so for b less than 0, then the negative b is actually bigger than positive b. So the ROC of the first part is to the right side of negative b, so kind of here, right? And the ROC of the second part is here, and they have no overlap, so there should actually be no ROC. So hopefully not too confusing. So the ROC is kind of the intersection of this side and this side, right? And there is no overlap, so yeah, so there is no ROC, and so the Laplace transform just don't converge anywhere. Okay. So this is an example of two-sided function. Why do I still have this? Okay. Yeah. So any question? And okay. Okay, so that's two-sided function, and then next we have example of we have two more property, and the first property says that we don't have proof. I guess we can give a very quick oral proof. So actually, oh yeah, okay. So for first property, property 7, it says that, so now this is also very strict. So we are back to the case where our x of t is, how do I, okay, let's do this. So back to a case where we are rational, and yeah, and we say our RC is one strip, right? So the boundary of a strip, so you probably already see from the examples, but this is also a property. So those boundary of the strips are always bounded by the poles, just like here, right? And so this is actually true for any rational big X Laplace transform. And so we don't have a proof here, but we are going to see later today that we can do the inverse Laplace transform for any rational function, and then it's very obvious that when you do the inverse, the RC are always going to be bounded by the poles. Okay. So it's either one strip, so it's either like this, one strip bounded by a left pole and right pole, or you can go to infinity, like from here go to infinity, or from here go to negative infinity. Okay. Okay. And then Then the next one is really not a new property, it's just combining property 7 with before. So it says that if you are still a rational function, okay, so let's do highlighter. So you are a rational function, then if you are also right-sided, then obviously your ROC is going to extend to plus infinity. So you should go from the rightmost pole, then go to plus infinity. Then if you are a left-sided function, then your ROC should go to negative infinity. So your ROC should go from leftmost pole, then go to negative infinity. Okay. So this is really just combining previous properties. Okay, so maybe let's see an example. Okay, should be quick. So we have a rational function. We are going to see many times. Big X of S equal to this 1 over x plus 1 minus 1 over x plus 2. Okay, so you can do partial fraction expansion, go to this. And so this thing has two poles at x equal to minus 2 and x equal to minus 1. And so as we say, ROC can be one strip. So then you have two poles that can be the cutoff point. So there are really only three possible ROC here. So it can be a right-sided function, and the ROC start from the right pole and go to plus infinity. And this one also has a good thing of, so if you have the Laplace transform back to x of t, yeah. So we have some extra property of x of t here. Here we are talking about x of t. So we think about x of t and doing Laplace transform. Then because this ROC including this sigma 0 part, so x of t, so this x of t will have convergent Laplace transform, Fourier transform. Okay. So here the important thing is this is Fourier transform. Fourier transform. Okay. And well, it's not a property we really talk about, so you can just remember this on the side. But anyway, so we are talking about ROC. So first possibility is equal to the rightmost, and from this rightmost pole, and then the other the other possibility is equal to negative infinity, so from the leftmost pole, or it can be the middle side, so between those two poles. Okay, and yeah, so here are something we're going to show in more detail in next class. So, but okay, we're about 1 minute, why not? So our x of s is really equal to this 1 over x plus 1 and 1 over x plus 2. And so this is in the form of the 1 over x plus a. And we know 1 over x plus a has two possible inverse, right? So the 9.1 and 9.2 depend on your ROC on left side or right side. And so you get 4 possibility, and 4 possibility got 4 overlap, right? So if you pick both ROC to the right side, then you will get this ROC, and you get a right-sided function. And if you pick both ROC on the left side, you get this one. And you pick this one to the right, one to the left, you can get overlap in the middle or no overlap then. Or no overlap, then it's invalid. Then yeah, then it's kind of invalid, and you don't get Laplace transform anywhere. Okay, and okay. Oh, sorry, a little over time. So we'll back in 10 minutes. Okay. Okay, let's get back. And okay, so we had our properties of ROC. So now you get a pretty good ideas of ROC. So for rational functions, it's going to be one strip. So you think about your rational function, then rational function you can draw the poles, and then the poles will divide your plane into strips. And for example, you have two poles, then you go to three strips. And well, sometimes you will have the same sigma, but usually you have n poles, you get n plus one strips. And so your ROC can be those strips that are separated by the poles. And also you can go to plus infinity or negative infinity. If those are the case, then your then your time domain function will also be right-sided or left-sided. Okay, and okay, so those are ROC, and then now we go to a kind of different topic, but actually related. So it's inverse Laplace transform. So we delayed this for quite a bit of time. So we always write our Laplace transform with the backend arrow. So that means that we get Laplace transform, we should be able to get the inverse Laplace transform. Okay, and so how do we do the inverse Laplace transform? We start with our derivation by using the Fourier transform. Okay, yeah. So we keep saying that Laplace transform in some sigma is just Fourier transform of x of t plus x of t times e to the minus sigma t. Okay, so we have this thing. Our Laplace transform at sigma plus j omega is Fourier transform of omega to x of t times e to the minus sigma t. So write out everything, then is x of t to the minus sigma t to the minus j omega t dt. And important thing is our sigma plus j omega should be inside ROC. Okay, and yeah, so this is what we know. This is our Fourier transform. But then now we can go back to our small x by doing inverse Fourier transform, because we know how to do inverse Fourier transform. Okay. And so that's what we do. We do inverse Fourier transform on these things, and we should get back to our x of t to the minus sigma t. And then you write down the equation. Inverse Fourier transform should be this 1 over 2 pi integral of omega from minus infinity to plus infinity. Then your big X as the sigma plus j omega inside your ROC, then times e to the j omega t. Okay. And so this is just doing inverse Fourier transform. And yeah, so then you can find the x of t then by just moving e to the sigma t to the other side. So you multiply e to the sigma t on both sides, then you get your inverse Laplace transform x of t is 1 over 2 pi d omega minus infinity plus infinity, and your big X times e to the sigma plus j omega t. And but this doesn't work for every sigma. Remember, your sigma needs to be in your ROC. This is important. Okay. And yeah, so this is the equation we have. And now you see this is sigma plus j omega, sigma plus j omega. Then you think maybe we should change this back to s. So we can change this back to s. So we change our variable. So remember the variable is omega here, then we back to some s. It's a bit weird, it's a complex variable now. So s equal to sigma plus j omega. And then s equal to sigma plus j omega, then ds equal to j omega. So the d omega is 1 over j times ds. Okay. And yeah, so then we have this equation. X over t is 1 over 2 pi j. Then your s. Now this is a different integral you might not see. So your s is integration from sigma minus j infinity to sigma plus j infinity, because you had your omega was just some real value from minus infinity plus infinity, but your s is some complex value from sigma minus j infinity to sigma plus j infinity, because that's what sigma plus j omega is. and then you have x of s times e to the st ds. Okay, and yeah, so you are integrating over a complex value line, and this is called counter integral. You are integrating over some line in your in your complex plane. Okay, so but let's see what this looks like first. So this is going to be a straight line like this. So you think about your h-plane, and you have some ROC. So maybe ROC look like this, and then the first thing is, as we said, your sigma should be inside your ROC. Okay, as we keep saying, and then your inverse Laplace transform is this integration of your line for some sigma inside ROC, then omega from minus infinity to plus infinity. So it's this straight line. Okay. And okay, so this is called a counter integral because not like before. So before we only have the usual integral where you are integrating a real value variable and in some interval on the real line. But now we are integrating on some contour on your complex plane. And well, we don't really know how to do counter integral, so this is kind of the end of here. So you can take a complex analysis class, and counter integral are actually quite interesting topic to learn. And but we will say a little more on counter integral here, and just for your interest. And so we are saying that the sigma need to be inside your ROC, but we didn't say which sigma. And that means that for any sigma inside your ROC, this your integral should give you the same result. And that's actually true. And why this is true is because some factor about counter integral we can talk about here. So the factor about counter integral is so you have now this contour on complex plane, and if you think about you have a loop, so maybe like a circle like this. So you are integrating over a loop, then the integration value depends on how many poles you circle in your loop, right? So maybe so if you get some pole inside, then you will get some value. But if you have no poles inside, then the integration will be 0. Okay, and so that means, and also a thing is if you are counter integral on like same contour but in a reverse direction, the integration is negative, and also you can break the integration into different parts, just like before. And so what this means that if you break this circle, like so if you break this at like 2 points, right? So you can think about breaking this circle at like these 2 points. Wait, I don't want that. Okay. So think about breaking the circle into this part and this part. So this plus this should be 0. Then if you reverse this part, that means if you you integrate from here to here, and you integrate from here to here, those integrations should give you the same thing. Because if you add this and subtract this, it should back to 0. It's a whole loop. Okay? So that means that if you are integrating over two contours that has same starting point and end point, and in the middle part there is no pole, then this counter integral should equal to this counter integral. And what this means is that if you are integrating inside this ROC, now remember we are okay, so let's assume we are doing rational functions, so they are easier. So we have that the rational function, the ROC, well, the ROC doesn't include any poles, right? Actually, this is true for even non-rational function. Okay, so the ROC should contain no poles. So you are doing this this straight line, and actually not even a straight line, even over whatever contour. And those should really equal to the same thing because it's like this case. But you have, so you are starting from negative infinity to plus infinity, and so usually what people do is you will get at the negative infinity, then you go like this, and you go like that at the plus and minus infinity. So you are thinking about you are doing this integral on straight line, or you go at infinity, and hopefully those infinity lines give you zero integration. So you're either from going integral on this line, then as soon as you at the infinity go to here, then you integrate on this weird line, then at the plus infinity you go here. So those two congruent should be the same, and this infinity part should also go to zero for some reason. And so that means this real line and this straight line should be the same. And the reason is because in your ROC you can also always in your ROC there is also always no poles, so you also always circle no poles, so you can kind of shift your contour around. Okay. So that's short introduction on contour integral. Any question? But sadly, we still won't tell you how to actually do contour integral. So let's do our second way of doing inverse Laplace transform. And this is kind of cheating. So what we do in the second way is we just consider the rational or the rational transformation. So that means our big X is rational. And so we'll just do our Laplace transform with something we've done many times. That is, we do partial fraction expansion, and we break them into these fractions of 1 raised plus a. Okay? And then we just look up our table, or like we just remember our example 9.1 and 9.2. Then we just say we know what's the inverse Laplace transform of x plus a, because we're already seeing that for different, so we're already seeing always inverse Laplace transform for the two different ROC. Okay. So yeah, that's what we do. We assume for the rational transformation, we just do partial fraction expansion. Then we look up our Laplace transform table, and just do reference to our table and do the inverse Laplace transform. So for now, we assume that even more for so as we know from partial fraction expansion that if you are unlucky, then you can get s plus a to some power. But as starting cases and examples, let's assume we are in a very easy case. So there is no a multiple, there is no higher power, and we are just break up to this perfect big A over s plus a. And then we have this form, then we just do inverse Laplace transform for every term. Okay. And as we said, then it depends on which ROC you pick. So this thing has a pole for every I, it has a pole at a, minus ai. And as we know, if ROC is to the right side, then you should pick this right-sided function equal to minus ait u of t. And ROC to the left side, you should pick the left-sided function equal to this minus e to the minus ait u of minus t. Okay. So that's really it. And okay, so we might finish early today. It should be fine. Yeah. Yeah, that's really it. And so the only hard part now is you need to decide whether your ROC is to the right of your pole or left of your pole. So let's see our examples. And we back to this function we were seeing before, is x of s equal to 1 over s plus 1 and times s plus 2. And okay, so as we said, so this is, let's go back to seeing it, is this thing, and we really say you can have 3 possible ROC. and we start with this one. Okay, and so we say the ROC is the real part of AC is bigger than -1. Okay, and we are going to pick our partial fraction with either the ROC right side or ROC left side thing. Okay, and anyway, so we start with partial fraction expansion, and here we give a short review of partial fraction expansion. So we want to break this 1 over s plus 1 times s plus 2 to something over s plus 1 plus something over s plus 2. And as we say, you can just multiply all everything and solve for a plus b. But here we also teach you something a little smarter, maybe a little faster. That is, you can multiply both sides by, say, s plus 1. Then you multiply both sides by s plus 1, and then this side will become 1 over s plus 2. And this side will become a plus this s plus 1 b over s plus 2. So why do we want to do this is because you look at this thing, and okay, so you look at this part, and you put s equal to -1. Then s equal to -1 and this s plus 1 becomes 0, so this b term just disappears. So you get left with this a term here. So a will be this 1 over s plus 2, taking at s equal to -1. Okay, so then I give that a equal to 1. And similarly, you can multiply both sides with s plus 2, and then you set s equal to -2. Then you get b equal to -1. Anyway, so these are, anyway, you can also do multiply out, etc., and get a and b. So we know, we kind of, so just like we know before, big X is 1 over s plus 1 minus 1 over s plus 2. And then now we need to think about what's ROC. Okay, so we have the whole function, we are picking the ROC or being the right-sided. The RES bigger than -1. Okay, so let's see picture. So we are picking this ROC bigger than -1. And then we know this is overlapping of two, this should be the intersection of the two ROC. So those two things has a pole and -1 and -2. And we think about what kind of overlap can give you this right-sided ROC, and the result can only be you pick this one being right-sided and this one being right-sided, and the overlap will be this thing, right? Okay. And yeah, so there's a lot of work here, but it's really just saying this. Yeah. So your ROC is to the right side then. So your ROC is the right side to both pole, and so you should pick a right side for both pole. Right side ROC for both pole. And yeah, so you have a right side ROC for both pole, and you should pick those two. And yeah, and so your inverse Laplace transform is this right-sided exponential decay e to the minus t, e to the minus 2t. And yeah, so then you do a linear combination of those two together, you see that the time domain is this thing, and well, time domain has no ROC. So yeah, it's just this right-sided function e to the minus t minus e to the minus 2t, u of t. Any question? Yeah. So yeah, so we have ROC on this, then we think is ROC on the right side or left side of this first pole, and it's on the right side, so we think ROC for the first pole equation, first pole part should be the right side, and level right of the second pole, and it's also right side, so both of them right side, you pick a right side. And then, as we said, there are three possible ROC, so let's see the second one. So the second one, we pick left-sided ROC. Okay, and I believe we don't have a picture here, but hopefully we can imagine. Maybe so we have time, so maybe I'll draw a little bit here also. Okay, so ROC is now on the left-sided, right? left side of both of the poles. Okay. Okay. So ROC is on left-sided, and as before, we can break this thing into our 1 raised plus 1 minus 1 raised plus 2. And wait, yeah, get it right? Yeah, okay, yeah, and yeah, it's left side of both poles, so obviously, so for the both friction, you should pick the left-sided ROC. So for the friction of this -2, you pick the left side, and the friction of this -1, you pick the left side. So you get those two left-sided exponential decay e to the minus b, sorry, e to the -1 minus t, so u of minus t, and then e to the -2t, 2 from these two, and then u of minus t. Okay, so you pick both of them to the left side, and then we double check if we have the ROC of this, let's say -1 less than -2, then the intersection is less than -2, so that's good. And yeah, and then the time domain signal is just a linear combination of those two things. So it's minus e of minus t, and then negative plus positive, and plus e to the minus 2t u of t. Okay. And finally, we have the middle part of ROC. Okay, so then now things get a little bit different. Let's see, where do I draw? Maybe here. So our ROC is in the middle side, right? Yeah, and now we need to be a little careful here. Yeah, so the ROC is in the middle side, so it's to the right of this -2 pole and to the left of this -1 pole. Okay, and why do I? Oh, okay, yeah, so we just have the answer here. So it's to the right of the -2 pole, and so then the -2 thing get this right-sided exponential decay, and it's to the left of the -1 pole, and okay, so let's write this again. We should have this everywhere. So our big X of S equal to 1 raised plus 1 minus 1 raised plus 2. Okay. So yeah, so there is a -2 pole correspond to this 1 raised plus 2, and there is a -1 pole correspond to this 1 raised plus 1, and there is a to the right side of this -2, so this -2 should become this right side exponential decay. It's to the left of this -1 pole, so this should become this left side exponential decay. So this is your X over T. Okay, and so yeah, so that's how you do inverse Laplace transform for rational transformations or rational functions of S. And obviously, if you have higher order term, then you need to be smarter using the higher order formula that we'll see maybe later. And also, let's go back to this table. So we get 3 of the things in this table, and as we said, there are 4 possibilities of choosing left and right of your 2 fractions, but only see 3 actual ROCs, because if you choose the left of the left and the right of the right, then there is no overlap. So that's not actually a valid Laplace transform anywhere. Okay. And yeah, so you get those 4 possibilities, and 3 of them correspond to 3 ROC. Okay, and we have extra time, but I think. Okay, so let's finish a little extra thing, and we will finish early today. Okay. And finally, there is some extra thing about this partial fraction expansion. well, obviously there are higher order terms, but there is also when your numerator has more power than the denominator. And as we said, then you will get some extra polynomial in the front. Okay? Yeah. So we need to do long division first, and then we'll get some extra term. So we get some polynomial s in the front. Then the other thing you can do partial fraction expansion into this 1 over s plus a. And so we need to, so why do we say this is because you have those extra polynomial of s, then we need to do their inverse Laplace transform. Okay? So what's the Laplace transform of polynomial of s? First is we can have the constant term. The constant term, we have this fact that you have your x of s is 1, then the inverse Laplace transform will be delta of t. So, yeah. And this, let's see, this you can just verify from basic Fourier transform, right? So this is like the Fourier transform, inverse Fourier transform of 1 is the delta function. Okay, and okay, so that's 1. So this is already a little weird because it's the delta function. And now I think about what happens if you have a higher order of s. And actually, then you can use properties that we didn't talk yet, but you can kind of guess. That is, you take a derivative on a time domain, then you will get extra factor of s in the s domain, or I guess not quite frequency, in the s domain. So you can derive this just like before. You do derivation of t on both sides with your Laplace transform equation. You see that you take a derivative on time domain, you get extra s on the s domain. And that means that the inverse Laplace transform of the s to the nth power is the nth derivative of delta function. And those are really weird things. Those are the singularity function. We call them u of n. Okay? It's the nth derivative of delta of t. And yeah, so this really complete the Laplace transform of everything. Unfortunately, you get a lot of singularity functions. So the constant term give you delta function, and nth power, s to nth power give you u of n. And just a little reminder about all the singularity functions. So we have delta function is like a limit square root equals 0. This really thin rectangular, and if you think about take the derivative of this thing, then you get like two very close spikes. So it is a one-time derivative of this thing. It's really weird, and but we kind of use the definition, operational definition of this is if you convolute some function with this u1 of t, then you are doing a derivative on your x. Okay. And then you can do this more times. So if you have a u1 convolute with u1, then you will get u2, and that's two times derivative of a delta function. And if you convolute some whatever function with u2, then you get a second derivative of your function. And if you do this k times, you get uk, etc. Okay. I think we are okay on schedule. So let's stop here for now. Any question? Otherwise, we'll stop early today. And next time we'll go to interpretation of Laplace transform and maybe some properties. Okay? Yeah. We talk about a lot of things about ROC. Okay. Okay, so no question, then see you next time.之前应该都出过了。
因为这边是这就是后面刚刚讲的都是正常的，
那应该是写错了。我确认一下，看一下，可是他是写错的。
对，我也觉得他这边偏向写错。
不知道为什么会错，可是看起来就是错了。好吧，那我觉得他应该是错了，他应该是他后面的也忘记符号。
对，后面有，这是他附题的 case 上，因为我附题的 case 上。
我觉得应该是写错了。
这样子，
我应该是，我会把它修正一下。我先上去再修好了。从日进入了。可以这样算，前段感觉教够多了，碰着昏头，上班很快。你好，离开不在应该是。我看预报好像刚好现在要下雨，在晚上，只是晚上会不会再下一次啊？我是不是应该现在赶快跑回家？
看一下其他地方。
手机预报现在都还蛮准的。早上还大雷雨预报。OK， 好，那先这样，拜拜。